In this discussion, we would look at the possibilities with the Vedic math. We would see the highlights where Vedic math really shines, some of the examples. These examples and the cases we study here are not exhaustive, but is sampling. I'm Sarwan Agrawal. I'm a Vedic math teacher. Do a brief historical background. The system was developed by Bharti Krishna Tirtha ji. There are 16 main sutras and 13 sub-sutras in this system of mathematics. According to Tirtha ji, this system is applicable to all field of mathematics, pure and applied. And Kenneth R. Williams has a book on astronomical applications and tricks using the sutras. Tirtha ji lived from 1884 through 1960. This is one of his pictures. Some more historical background. Vedic system was reconstructed between 1911 and 1918. Bharti Krishna wrote one book, volume in Vedic mathematics. The book was published in 1965. Let's continue. Tirthaji was Sankaracharya of Puri Math. This is another of his picture. So here are the sutras we have been talking about. 16 sutras on left, they are the main sutras, and sub-sutras 13 on the right. The sutras are described as Sanskrit words followed by its English translation. And same is true on the right side for sub-sutras. Okay, let's continue. Now let's look at examples here you can do. We have a sutra, square of number ending in 5. So, and sutra is by one more than one before. So if I say 15 times 15, we're trying to do a square of 15, and number on left matches, and 5 and 5 are 25. That's the result on the right. On the left we have by one more than one before. So 1 times 2 on left. So 15 times 15 is 225. Similarly, 25 times 25 is 625. 25 on the right, 5 times 5 on the left, 6. 2 times 2 plus 1. 2 times 3 is a 6. Similarly, you can do 35 times 35, 45 times 45, 95 times 95, and so on. Okay, let's go do something else here. Let's go to last column here. We know that 25 times 25 is 625. So 0.25 times 0.25 must be 0.0625. So 0.25 has 2 digits after the decimal place, and this one has 2 digits after the decimal place. The result must have 4 digits after the decimal place. So 0 is required. Now let's see what we did just right now. 25 is a 1 quarter. This is 1/4 again. 1/4 times 1/4 is 1/16. We just converted 1/16 to its decimal equivalent. Let's do this 125 times 125, which would be 25 on the right and 12 times 13, which is 156 on left. So it's 15625. If you come back here, 0.125 times 0.125 must be 0.015625. Extra 0 we need because 3 digits after decimal here and 3 digits here. We need 6 digits after the decimal in the result. So we got an, okay, this is 1/8, this is 1/8. So 1/8 times 1/8 is 1/64. So we just converted 1/64 to its decimal equivalent. Similarly, you can do 0.35 times 0.35 and 5.5 times 5.5. And here's a variation here. When we were doing 15 times 15, number on left digit was matching. On the right, the 5 plus 5 is 10. if you were to reverse those digits, say 51 times 51, where 5 plus 5 is a 10 and 1 matches on the right. Okay, so 5 plus 5 is 10 and 1 matches on the right. So there, in that case, it's slightly different. On the right, it is still 1 times 1, but it's 0, 1 because, uh, okay, it's a 0, 1. On the right, it's not 5 times 6. On the left, it's not 5 times 6. Instead, 5 times 5, which is 25 plus 1 from the right. 2601. Okay, we need this 0 here is 1 times 1 is a 1, but I need 0, 1 here because this is 50 times 50 kind of with 2500, and this is 1 after that, so 2601. So 52 times 52 on the right is a 2 times 2, which is 4. Actually need a 0, 4 here. On the left it is 5 times 5 plus 2, 27. Similarly, the others you can do. And look up some more examples here on the right here. 33 times 37. It's a 3 matches on the left. On the right, 3 plus 7 is 10, just like 35 and times 35. In this case, on the left, it's by 1 more than before. So 3 times 4 is 12. On the right, it's 3 times 7. So answer to 33 times 37 is 1221. Okay, similarly 54 times 56 is 24 on right and 30 on left. 77 times 73 is 21 on the right and 7 times 8 is 56 on the left. 325 times 375 here, two digits here, 25 and 75 add up to 100. So it's 3 times 4 is a 12 here on the left. On the right is 25 times 75. I say 1875. You could split that 25 times 75 to be 25 times 3 times 25, and 25 squared is 625. Then 625 times 3 is 1875. So it is 1, 2, 1. Alright, we're going to do a cube root of a perfect cube. Sutra we are going to use is by observation. We are going to observe this table on the left. This is my reference table. It has two columns, one on the left, one on the right. Left column has numbers 1, 2, 3, 4, 5 until 12, and right column has their cubes. Cube of 1 is 1, cube of 2 is 8, cube of 3 is 27, and rest of them just like that. Example I'm going to take is 103,823 cube root of that number. 103,823 is a perfect cube. Okay. When do cube root, we divide into groups of 3. So we split 103,823 in 2. 823 on the right, rest of them on left. Then I look at 3 rightmost digit and come back in the table. 3 is against 7. Cube of 7 has a 3 in the end, last digit is. From that I know that 7 is the units place of cube root of 103,823. For left digit of the answer is, we look at 103, the left group, come back in the table. 103 is between 64 and 125. Cube root of 64 is a 4. That gives me that 4 is leftmost digit of the answer. So cube root of 103,823 is 47. What we did is split in two groups. 3 digits on the right, rest of them on left. Look at the rightmost digit to find the rightmost digit of the cube root, and look at this left group and identify the two cubes that encompasses this 103, and take the smaller cube root. Okay, 64 and 124, 5. Cube root of 64 is a 4. All right, now let's go try some more examples from the list here. 2744. 4. First we split in two groups, right group and left group. Okay, then we take 4 here, come back in table. 4, cube of 4 is 64 and has a 4 in the rightmost digit. So cube root of 2744 has a 4 in the units place. Now we, for the tens place answer of the cube root is, look at 2 here, come back in the table. 2 is between 1 and 8. So that gives me that cube root, 10th place answer for cube root is 1. So that gives me 2744. Cube root of 2744 is 14. Let's try another example here. 1560896. Split in 2. Right group has 3 digits and rest of them on left. So from rightmost is 6. Come back in table. Cube of 6 has a 6 as rightmost digit. That gives me that 6 is the rightmost digit of the cube root of 1560896. For the left digits, look at 1560. Come back in the table. 1560 is between 1331 and 1728. That gives me 11 are the left digits of the cube root of 1560896. That gives me cube root of 1560896 is 116. Let's look up another cube root here. 238, 328. Split in 2 groups. Look at last most digit 8. Come back in here. 8 comes against 2. That means the units place of the cube root of 238, 328 is 2. Now look at left group 238. Come back in the table. It's between 216 and 343. That gives me left digit of the cube root as 6. So cube root of 238, 328 is 62. So by the method we just discussed and referring this table on the left, you can find cube roots of 1 cubed and 119 cubed. Now we would do near base multiplication. It's kind of special multiplication when operands are close to a base number. The sutra we would use here is all from 9 and last from 10. Example we use is 998 times 817. Okay, and in conventional math, first line is multiplicand, second line is multiplier. So we multiply the multiplicand by the units position digit of the multiplier, which is 7. So it says 998 times 7 is 6986. Then we take the next digit of the multiplier, which is 1. Multiply that with the multiplicand 998. So we write 998, but the second row here we shift that to the left by 1 place. Next we take up next digit of the multiplier, which is 8. Multiply 8 with 998, which is 7984, and then we shift this 7984 by 1 more place to the left. Then these 3 numbers here, here's 1 0 here and 2 zeros in this line here. We add them together and the answer is 815366. Through this process, we have multiplied 998 and 817 and I get an answer of 815366. In Vedic mathematics, we'll write down the 2 numbers involved in multiplication, 998 and 817. Then we pick up a base number, which is 1000 here we picked up. 1000 is very close to 998 and it's not too far from 817. Then after that, we draw a vertical line to the right of the number. Then next, we write a minus 002 against 998. We obtain minus 002 from 998 minus 1000, which is base number. Similarly, we obtain minus 183 from by 817 minus 1000. Subtract 1000 from 817. In these subtractions here, we can use the sutra all from 9 and last from 10. Now the multiplication part is easy. On left side, we cross apply this deviation here. Deviation is minus 002 of 998 and minus 183 is of 870. So we're going to cross apply and operation involved is minus here. So it's 817 minus 002, which is the number on left, 815. 815 is part of the answer. You can obtain 815 by using the first operand here, 998. So we cross apply the deviation here, 998 minus 183. See this minus here, they got applied here, 998 minus 183. That's also 815. On the right side, we vertically multiply the deviations. So 2 is one deviation, minus 2, and minus 183 is the other deviation. We multiply them together vertically. Answer is 366, and minus multiply together to get a plus. Answer is 815366. As long as number of digits on the right side are equal to number of digits in the base, number of zeros in the base number, we can just write down 8, the answer as left part 815, right part 366. So another thing is, in addition to being 3 digits and 3 zeros here, sign has to be positive. So 815 is on the left, 366 is positive on the right. We can see answer is 815 and 366. Okay, but you can always do that. Left part times base, which is 1000, plus right part is 815366. When you multiply by 1000, that adds 3 zeros to 15, and this 366 from right just slide into those 3 zeros, and the answer is. Now we are going to do some examples here for base multiplications. First example is 98 times 98, and the two numbers are close to base number 100, and 98 is 2 less than 100, so is the other 98 is 2 less than 100. So when you cross apply the deficiencies on left, it's 98 minus 02. On the right, when you multiply vertically the deficiencies, minus 02 times minus 02, and answer is 9604. 96 on the left, 04 on the right, it's 9604. 98 times 98 is 9604. Let's try an example of 102 times 103. Base number is again 100, and left operand is 2 more than 100, and right operand is 3 more than 100. When you cross apply the efficiencies or surpluses, we get 102 plus 3 on left, which is 105. On the right, you get 02 times 03, which is 06. And 102 times 103 is 105,006. It's 10506. 999 times 999 is, this is 1 less than 1000, and this is also 1 less than 1000. Convenient base for this multiplication is 1000. So on left we do cross applying deficiency, which become 999 minus 1, which is 998. On the right, we vertically multiply the deficiencies, which is 001 times 001, which become 001. So 999 times 999 is 998001. So if you go to multiply 9998 times 9997, convenient base is 10,000. First operand is 2 less than 10,000. Second operand is 3 less than 10,000. So when you cross apply the deficiencies on left, become 9998 minus 3, which is 9995. On the right, we got 0002 times 003, which is 0006. So 9998 times 9997 is 9995 0006. So if you do it, 143 times 999, first operand is 143, which is 857 less than 1000. Second operand is 999, which is 1 less than 1000. So we do 143 minus 1, which cross applied the deficiency of the other number. 143 minus 1 is 142. On the right, vertically multiply the deficiencies, become 001 here and 857 from here. So 857 on right. So 143 times 999 is 142857. So using base multiplication, you can do multiplication like this, in most Now we would discuss dividing by base number. We would use Nikhilam method, and also called transpose, transpose and apply method. And example we would use is 12034 divided by 9. So for conventional match, set up the problem like this: 12034, then vertical line and 9 on the left. Then take the first two digits, divide by 9, and you take quotient of 1, a remainder is 3. Then bring down the next dividend digit, become 30, and then you next quotient is 3, then 27, and 3 is a remainder. Then bring out the next dividend digit, make it 33 for current dividend, divide that by 9, so get 3 here, and the 27 again, remainder 6, bring down next digit, 64, then quotient is 7, 7 times 63, remainder is 1. So after we went through so many steps, the answer was 12034 divided by 9 is 1337, remainder 1. In Vedic math, we just like as usual, just say 12034 divide by 9. We consider a base number which is closer to 9, which is 10, and its deficiency or deviation from 10 is 10 minus 9 is 1. We call deficiency is 1. Okay, so first we do is mark down a rightmost column here, draw vertical line to the left of rightmost digit here. That's like dividing by 10. So if we were to divide by 10, it answer would have been 1203, remainder 4. But we are actually dividing by 9 instead. So for that, adjustments are: first bring down the first leftmost digit of the dividend, that's 1 is the leftmost digit of the quotient. The next is add this dividend digit to the next, add this quotient digit to the next dividend digit. 1 plus 2 become 3. 3 is our next quotient digit. Add that quotient digit 3 to the next dividend digit 0. 3 plus 0 is 3. That's our next quotient digit. Add 3 to next dividend digit, and 6 is our next quotient digit. Add 6 to the next dividend digit, and 6 plus 4 is 10, remainder is 10. In division by 9, remainder 10 is too much of remainder, so we divide 10 again by 9 with the 1, remainder 1. The 1 we add to the quotient here, and the quotient become 1337, a remainder is 1. So answer is 1337, remainder 1. We achieved this division by adding the digits in the dividend. We just when the remainder was more than 9, and 9 or more, we took out the 9 from remainder and added that to the quotient. So we divided that remainder of 10, which is at least 9, and get a quotient of 1, which the quotient we added to the quotient, and remainder 1. So 1337, remainder 1. Okay. Let's do some examples here. 1, 2, 3 divided by 9 is, first is 1, then 2, 1 plus 2 is 3, 3 plus 3 is a 6, so it's 13, remainder 6. So 1, 1, 1, 1, and divided by 9 is 1, 2, 3, remainder 4. So 1, 2, 1, 0, 2, 0, 3 divided by 9 is 1. Then again 1, 1 plus 2 is a 3, 3 plus 0 is 3. So 1, 1, 3, 3, remainder 6. 1, 1, 1, 1, 1, divided by 9 is 1, 2, 3, 4, remainder 5. Now 6 ones is 1, 2, 3, 4, 5, remainder 6. 7 ones are 1, 2, 3, 4, 5, 6, remainder 7. 8 ones is 1, 2, 3, 4, 5, 6, 7, remainder 8. Now 9 ones here. 1, 2, 3, 4, 5, 6, 7, 8. Remainder 9. So 9 is too much of a remainder. So we divide 9 by 9 again to get a quotient of 1, remainder of 0. And the quotient get added to the quotients we had. So answer is 1, 2, 3, 4, 5, 6, 7, 9, remainder 0. So we have sequence of 9 ones divided by 9. We got a 1, 2, 3, 4, 5, 6, 7, 9, and remainder 0. So it has number of 1 through 9 and 8 is missing. Now we would try to compute 1 over 81 and use the information we just learned. Note that 81 is 9 times 9 and 1 over 9 is 0.1 recurring. So 1 over 9 is 0.1111. 1 over 10 is exactly 0.1 and 1 over 9 is 0.1 repeating. So 1 over 81 would be 1 over 9 and the another 1 over 9 was 0.1 recurring. So it is equal to 1 over 9 times 0.1 repeated as many times as we need. So we just take a 9 ones here. That gives me a 0.012. So we know that when we divide one sequence of 9 ones, we get a 1, 2, 3, 4, 5, 6, 7, 9. But I need 9 digits here because we started with 9 digits after the decimal. This is 0 here, 0, 1, 2, 3, 4, 5, 6, 7, 9. Then it's recurring because this series have as many ones as I care to. So I can take another sequence of 9 digits, 9 ones after that and get in it another 0, 1, 2, 3, 4, 5, 6, 7, 9. So we just computed 1 over 81 by dividing twice by 1 over 9, 1 by twice by 9, and first time we did is we used that result here. Then second time we did divide is we used that when we divide a sequence of 9 ones, we get in 0, 1, 2, 3, 4, 5, 6, 7, 9. We would do that 1 over 81 again. This time we would really construct this thing. Okay, 1 over 81 is we multiply and divide by a sequence of 9 ones. So 1 divided by 81, numerator is 1 times 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, divided by 81 times the same sequence of 9 numbers. Okay, so we factor this thing out in numerator. It's 9 times 1, 2, 3, 4, 5, 6, 7, 9. We know that when we divide sequence of 9 ones by 9, we get in 1, 2, 3, 4, 5, 6, 7, 9. So R1, 2, 3, 4, 5, 6, 7, 9 is a factor of the sequence of 9 ones, and the other factor is 9. In denominator, we say 81 is 9 times 9, and one of the 9s we multiply by sequence of 9 ones. Okay, so that is when we multiply sequence of 9 ones by 9, we come a sequence of 9 nines. This 9 and this 9 cancel out, so we are left with 1, 2, 3, 4, 5, 6, 7, 9 divided by sequence of 9 nines. And this has 8 digits, numerator has 8 digits. We add a 0 to the left to make a 9-digit sequence on the numerator and a 9-digit sequence of all 9s in the denominator. And that's the definition of recurring numbers, and that is 0 0.0, 1, 2, 3, 4, 5, 6, 7, 9 recurring. If you were dividing by 1 forward 3 zeros, 1 forward 9 zeros, we would have gotten a exact 0 0.0, 1, 2, 3, 4, 5, 6, 7, 9. But we are dividing it not from by 1 forward by 9 zeros, instead by sequence of 9 nines. So that gives me recurring numbers. So that means you see that similarly, if we were to do 1 over 9801, 9801 is a square of 99, just like 81 was a square of 9. We would get 0.0001, 02, 03, 04, all the way up to 97 and 99, and recurring number 98 would be missing. Okay. I would show you, you can extend the same division we just used to compute 1 over 998,001. First note that 998,001 is 999 times 999. That's our near base multiplications, and 1 over 999 is 0019999, and that is a fractional equivalent of the number 0.001 recurring. So that means 1 divided by 999 is 0.001 forever. So, but we're trying to do 1 over 998,001. That means I could divide 1 over 999 again by 999. Okay, and method we're going to use is 999 is close to a base 1000, and its deficiency from 1000 is 1000 minus 999, which is 3-digit deficiency is 001. We need 3 digits because base 1000 has 3 zeros. So the method we use is first we divide by 1000, and that means we're going to move the decimal place 3 digits to the left, and that's right here. We have 001, 001, 001 reckoning and so on, and then we add 3 more zeros to the left and move the decimal place right here. Adjustments is we bring down this dividends into quotient line, and as soon as we get a non-zero dividend digit which I bring to quotient line, I add 1 times the deficiency 001 to the next 3 digits. So this becomes 2 here in this quotient digit. Then this quotient digit becomes, so we add 002 I add to next 3 digits. This quotient digit becomes 3, add 003 to next 3 dividend digits. So I got 004. So look at the pattern we are getting. 0.00, 0001, 002, 003, 004, so on. 990 up to like that. At the end we get 997, 998, 999, 1000, and 1000 has a carry. I got to bring that back to 999, which it becomes 1000. We take carry back, leaving a 0 here, so this number becomes 999. So 1 over 998,001 is 0.000, 001, 002, 003, and so on. 997, 999. 1000 has 3 zeros, and this recurring number has a groups of 3 digits each: 0, 1, 2, 3, 4, 997, and 999. 999 is the largest 3-digit number, so 1 before that is missing. Okay, now you should be able to do some more of these recurring numbers which are given by square of a number like sequence of nines, 1 over sequence of nines. Okay, we will try to compute 1 over 998,001 directly. First, we already knew that 998,001 is 999 times 999. I would need the 2 sequences here. One is 297 nines, which is sequence of nines of length 297. Another is sequence of ones of length 297. We know that 1 over 998,001 is a recurring number. And recurring numbers, its fractional equivalent have a sequence of nines. Okay? So there must exist a number n such that when I multiply and divide 1 over 998,001 by n, so 1 times n numerator and 998,001 times n in denominator, this denominator must be sequence of 297 nines. We know that from previous workout that the number of digits in recurring number was 297. Such a number n must be two sequence of ones of length 297. That's the one we defined before, because 297 is an odd number, and to get sequence of nines of length odd, we can obtain that by multiplying by 9 a sequence of ones of the same length. Okay. So let's see. Also note that 998001 is 999 times 999, which is, we need a 19 here to multiply by sequence of ones to get in a sequence of nines in denominator. The rest of that 9, 111 and 111 we have to cancel out from the sequence in the numerator. Okay. So so we have to cancel that out. Okay, so numerator is 1 times, where must is 1 times n, 1 times the sequence of ones. So it has 111, 111. So we can divide by 111, divide the numerator by 111, so becomes 001, 001, 001 all the way, and it still has a length of 297. We paired that with two zeros on the left to make sure that length of this number is still 297. In denominator, we cancel out one of the nines here, so we're left with 9 times 111. We have cancelled divided by 111, so we're left in denominator by 9 times 111, and this other 9 and 297 ones we still have. Numerator is of that length, and denominator is 9 times 111 times 9 times 297 ones. Now we're going to divide by 9, both the numerator and denominator. So numerator become, when we divide by 9, 3 zeros, 111, 222, so on. So you see the pattern. It's a 000, 111, 222, 333, 444, and so on. Because it carries, the details become messy, but the pattern is clear. Denominator is, we are going to divide by 9, so this 9 disappears. So we have 111 times 9 times 297 ones. Now, in denominator, we have to get rid of this 111 here. Okay? So we divide by 111, both the numerator and denominator. So we divide by 111, its numerator is 000, and 111 becomes 001, 222 becomes 002, and then 003. Again, carries make the details messy, but the pattern is still clear. So denominator is 9 times 297 ones equal 297 nines. So 1 over 998,001 is 000, 001, 002, 997, and 9. And then we know that 998 will be missing, so 999 recurring. If you go through details and work it out, you will make it work out fine. In this discussion, we had divided 297 ones by 111 times 9 times 111. We knew that after simplifying, we would get 000, 001, 002, 997, 999, okay, in the numerator. This is thus 111 times 9 times 111 must be a factor of sequence of ones of length 299, and other factor is 000, 001, 002, and so on. We parity with the zeros on the left to make sure the length is still 297. Okay, we will try to do a equation of line through two given points. The points are 7, 4 and 5, 1. The general equation is y equal mx plus c. In conventional math, first we compute m, which is the slope here, which is delta y over delta x, and is 3 over 2. You can look at the right angle triangle here between these 2 points. So for a change of value of 2 in x, y changes by 3, and so slope is delta y over delta x, which is 3 over 2. Okay, and so we just computed m. We substitute that m into the general equation here. So become y equals 3 by 2 times x plus c. We still need to compute c. For that, we substitute one of the points. Say we're going to substitute phi 1 into this equation where we don't know c yet. So that becomes 1 equals 3 by 2 times 5 plus c. That means there from there I compute c. c is minus 13 divided by 2. So m I already had, c I just computed. So the equation is y equal 3 by 2 times x minus 13 over 2. I can multiply out the equation by 2. That means 2 times y is 3x minus 13. So in conventional math, first I had to compute m, substitute m, then substitute one of the points and compute c, and then get my equation. In Indian math, we do it a little different. In Indian math, we use the sutra vertically and crosswise. We still have same 2 points, 7, 4, 5, 1. We still have same equation, y equal mx plus c. So first we do is write down these 2 points, one above the other, 7, 4 and 5, 1. We subtract vertically, 7 minus 5 equals 2. That's my y coefficient. Y coefficient is delta x, 7 minus 5 is 2. X coefficient I get from 4 minus 1. Vertically subtract, it's 4 minus 1 equals 3, that's my x coefficient. So far I have computed 2y equals 3x. C I don't know yet. For the constant term, I multiply crosswise and subtract. So 7 times 1 minus 4 times 5. 7 times 1 is 7, 4 times 5 is 20. 7 minus 20 is minus 13. So I have everything in here. So constant term is minus 13. The equation is 2 times y equals 3 times x minus 13. We did everything in one step. We subtract vertically to get my coefficients of the y and x, and multiply cross y and subtract to get my constant term. So 2 times y equals 3 times x minus. Okay, we will have some examples to work on to do the equation of lines. Here are 2 points I have for the first example, 2, 3, 3, 4. We can do this one just by observation because 3 is 1 more than 2 and 4 is 1 more than 3. So y equal to x plus 1 is by the equation of line for these 2 points. But just to prove that our sutra would get me same answer, let's go do the subtract vertically. 2 minus 3, that's minus 1. So we have minus y equals 3 minus 4, which is minus 1, equal minus x. Now the constant term, 2 times 4 minus 3 times 3, 8 minus 9 equal minus 1. So we have minus y equals minus x minus 1. And we can divide out the minus 1 sign, so become y equal to x plus 1. If we look at the other next point here, example here, 5, 6, 8, 7, 8, 7. So subtract vertically 5 minus 8, which is minus 3. So I have minus 3y here equals 6 minus 7 minus 1 equal minus x, and the constant term, 5 times 7, which is 35, minus 48 minus 13. So we have a minus 3y equals minus x minus 13, and cross out the negative terms, y 3y equal x plus 13. Here next example here is a 4, 8, 1, 2. 8 is twice as much as 4 is, 2 is twice as much as 1 is. So y is equal to 2x is the equation. It's y is always twice as much as x is. So let's go, we can do this one here. Y is equal to 4 is the equation. In these points here, 1, 5, 1, 7, x is equal to 1. You can do almost any equation of any line through any 2 points using this method. Okay, let's go to some examples where we can solve by observations. If x plus 1 over x is 17 by 4, which is of type 4 plus 1 over 4, so either x is equal to 4 or x equal to 1 over 4, they both are solutions to the equation here. So let's extend that. Instead of x, we have x plus 5 divided by x plus 6 plus x plus 6 divided by x plus 5 equals 113 divided by 56. It's of same type. It's a divided by b plus b divided by a. And these two factors, 113 plus 56 is 8 by 7 divided by 7 by 8. So if a divided by b is 8 by 7 like this, x is minus 13. If b divided by a is 7 by 8, if a divided by b is the other number here, 7 by 8, x plus 5 divided by x plus 6 is 7 by 8, then x is 2. So we first split that number 11356 into two, sum of two numbers of the type a divided by b plus b divided by a. So 8 divided by 7 plus 7 over 8. Then we equate this number a divided by b once to 8 by 7 and then to 7 by 8 to get two solutions here. Now let's look up equation of a line through these 2 points. Y is a constant, is 2, and equation is y by 2. Let's try to solve a simultaneous equation where x plus y is 9, x times y is 14. A factor of 14, it's either 1 times 14 or 2 times 7. 2, if I use 2 and 7 as a factor, 2 plus 7 is 9. So, and which satisfy the other equation too. So if x is a 7, y is a 2. If x is a 2, y is 7. They're symmetrical. Okay, now let's solve. There's a Samuchai Sutra we have, and there are numerous forms over there. So equation is 2x plus 5 divided by x plus 3, 6x plus 35 divided by 3x plus 17. Here, if you observe, n1 on this side and n2 on this side, n1 plus n2 is 8x plus 40, 8x plus 40, and denominator is 2x plus 20. They are equal except for a constant factor of 2. So we can say either 8x plus 40 is 0 or 4x plus 20 is 0. So 4x plus 20 is 0. That means x is equal to minus 5. So we have been able to solve these problems by observations and using some. Okay, we are now going to do a square root of a complex number, which is a little harder to do, but with Indian math we can do it easier. So example I'm going to take is 3 plus 4i, and for my notational help I'm going to use let a plus I times b be square root of 3 plus 4i. This is my assumed square root of the given number, which was 3 plus 4 times I. First step I do is make a right angle triangle with a base equal to 3, which is real part, 4 is a height, which was imaginary part, plus, and 5 is hypotenuse. This is my step 1. Make a right angle triangle. 3 and 4 are just from the problem here. Real part is the base, imaginary part is the height, and 5 is the hypotenuse. You get them from Pythagoras theorem. Okay. Now we get an A of the solution is the square root of base plus hypotenuse divided by 2. It's a base plus hypotenuse divided by 2. 3 plus 5 is 8 divided by 2 is 4. Square root of that is 2. That means A is equal to 2. We say A plus IB is a notational name for our answer of square root. So A, we already solved for A, which is 2. B is height divided by 2 times A. Height is 4. A we computed 2. 2 times 2 is 4. 4 divided by 4 is 1. So B is 1. Now, after use this Pythagoras theorem to compute 5 here, we know required square root is plus minus 2 plus 1 times I. Square root had two values, plus and minus. So this is how we say plus minus of 2 plus 1i. Alright, we just got them. We took 3 and 4, make the right angle triangle with the base equal to real part, height equals to imaginary part, and hypotenuse from Pythagoras theorem. Then A is equal to square root of 3 plus 5, 8 divided by 2. 3 plus 5 is 8, divided by 2 is 4, square root of that is a, and b is 4, which was the height here. 4 divided by 2 times a. We just computed a, so that's 2 times 2 is 4. 4 divided by 4 is 1. So imaginary part of the answer is 1. And required square root is again plus minus of 2 plus 1 times. Now we will see some examples here. I'll see some of the examples which are known right angle triangles with all the sides are equal to a integer values, whole number. 7, we will pick up a 7 plus 24i for my example to practice the method we just learned. 7, I'm going to make a base and 24 as a height. And now to compute a hypotenuse, I say 7 squared, which is 49, plus 24 squared, which is 576. 576 plus 49 is 625. Square root of that is 25. So my right angle triangle is base 7, height 24, hypotenuse 25. For real part, I say 7 plus 25, which is 32, divided by 2, which is 16. Square root of that is 4. So real part of the answer, square root is 4. Now I'm going to divide 24 by twice of the 4. 24 divided by 8 is 3. 3 is the imaginary part of the answer. So square root of 7 plus 24i is 4 plus 3 times I is a plus minus of 4 plus 3 times I. Okay, now let's go look at another example Now we will look at another way to do square root. A complex number a can be given by r times exponent of minus I times angle. R is the magnitude and angle is the angle between x-axis of the hypotenuse. Okay, so square root, if you need to look at the complex number given by this r times exponent of minus I times angle, real part of complex number is r times cosine of angle, and imaginary part of complex number is r times sine of angle. You can use these two parts, this as a base, that's a height, and use the previous method we studied, but we are going to do this one here. Square root of a is given by square root of r times exponent of minus half the angle. So we have to take a square root of this thing and half the angle we got to figure out. Okay? So we would try to make a right angle triangle with half the angle, okay, with the hypotenuse, and where hypotenuse is equal to square root of r, what we need. Okay? So we're going to make a right angle triangle with half the angle and hypotenuse equal to square root of this r, and that real part of the answer would be the base, and imaginary part of the answer would be the height of the triangle we would make now. Okay? Let's see an example, and let's do the square root using an example. Example is 15 plus 8 times j. 8 is the imaginary part, a real part is 15, and if you make a right angle triangle, 15 as a base and 8 as a height, its hypotenuse, which is r in the previous setup, which would be square root of 15 squared plus 8 squared. 15 squared is 225, 8 squared is 64, 225 plus 64 is 289, square root of that is 17. Now to make a right angle triangle with half the angle, we'll do extend the base by the positive extent of the hypotenuse 17. 15 plus 17 equals 32. New right angle triangle with half the angle has a base of 32 and same height at 8 here. Okay, and we don't really need to work with a right angle triangle of base 32 and height 8 to get an angle. We can use a similar triangle, and similar triangle would have exactly same angles. So if I divide height and a base by 8, we get a similar triangle with a base equal 4 and height equal to 1, and from that we have, and its hypotenuse is square root of 17, and that's what we need for hypotenuse. So answer is square root of 15 plus 8j is plus minus of 4. We just computed 4 here and 1 here plus 1 times j. So we were able to compute the square root of this number without doing any square roots of the, we didn't have to divide it by 2 and take a square root like we did before. We did all that by construction. For references, Vedic Math by Tirthaji and Triples by Kenneth R. Williams would suffice, would cover most of the topics we covered in here.